Hello all, welcome to Advanced Engineering Physics, Quantum Mechanics Part 9. So this is Dr. S. Deepthi, Assistant Professor in Physics, Department of H&S, MLR Institute of Technology. So what we are going to see, in this video lecture, we are going to observe the formation of energy bands and origin of band gap. In the previous video lectures, we have learned about EK diagram and effective mass of an electron. Okay. So what is EK diagram? We saw about the allowed energy states and forbidden energy states and so on. Okay, there we have already learned about how the nucleus attracts the electrons of another nucleus when two atoms come close together and so on. So here in this video lecture, in detail we are going to learn about the formation of energy bands and origin of band gap. Okay. So see here. Individual atoms in solids are held together securely by interatomic forces and bonds. These forces are primary reason solids maintain different shape and volume. Okay. The nature and strength of this bonding are strongly dependent on the electronic structure of atoms involved. The configuration of electrons dictates how the atoms interact. So, okay. The nature and strength of this bonding are strongly dependent on the electronic structure of atoms involved. Okay. So, in solids, countless atoms are brought together in close proximity. This is what we have already learned. So, in detail. Now, because of this interaction, the sharp and discrete energy levels of isolated atoms split into a set of bands containing very closely spaced levels. This is what happens here. This phenomena transforms electronic landscapes from single lines to broad zones of allowed energies. Okay. So, single lines, that means, single lines means the energy levels. The energy levels for an atom, this is the, let us consider this is the nucleus and this is the, what we are called as bands. Okay. Or, the different orbitals. Okay, orbitals we can say as different orbitals. So for an atom, a nucleus is there and different orbitals will be there and electrons will be revolving in the different orbitals and electrons are set in different orbitals according to Pauli's exclusion principle. This is what we have already learned. So what happens here? According to the Pauli's exclusion principle, when forces are balanced, two atoms occupy the stable position. And no two atoms have the same quantum state. This is the Pauli's exclusion principle. When multiple atoms come close together, 1, 2, 3, 4, there are 4 multiple atoms come close together, what happens? The energy band formation in this way. The energy bands are formed in a particular sequential manner. The energy bands will be formed in a sequential manner. When these atoms come close together, the nucleus of one atom, see, once again, look here. This is the nucleus of one atom, attracts the energies of orbitals of another atom, and so on. This will attract this one, this will attract this one, and so on. Due to this attraction of opposite orbitals by the nucleus, we are going to have the energy bands. And due to the attractions of some nucleus may attract more, some nucleus may attract less. Due to the differences in the attraction, we are going to have the forbidden gaps. We are going to have the bunch of these orbitals come close together to form energy bands, and a bunch of another orbitals come close together to form into another energy bands with a forbidden energy gap. Okay. Now, this is the origin of energy band gaps. A single sodium atom has 11 electrons. This is the example. The structure of sodium atom of Z has 11. Z is equals to 11. Its electrons are arranged in a distinct energy levels around the nucleus. Electronic configuration is 1s2, 2s2, 2p6 and 3s1. The single electron is the outermost electron in the 3s shell, which is the valence electron responsible for bonding and conductivity. So, just we are going to have the, before going into the origin of band gaps, let us have just an outlook of sodium atom. A sodium atom consists of 11 electrons, of which only one electron is the valence electron. Okay. Now see here, in a crystal, let us consider there are n number of electrons. These atoms come close together to form a crystal. The potential of one atom distributes the energy level of with the neighbors. This interaction is a fundamental level of energy causing. Splitting of energy levels depends upon the Pauli's exclusion principle. You need to remember this one also. When orbital overlaps, the single energy level of an isolated atom splits into n closely spaced distant levels to accommodate the electrons. Okay. So, how the splitting of energy levels occurs? Splitting of energy levels depends upon Pauli's exclusion principle. When the orbital overlaps, the single energy level of isolated atom splits into n closely distinct levels to accommodate the electrons. Okay. The inner shell electrons bound to the nucleus and the outer bands can overlap in the energy at the equilibrium distance. So, what happens here? Inner electrons never participate in the distribution of energy levels. Only the outer bands or the outermost bands which are far from the nucleus take part in the distribution of energy levels. So, see here, interatomic space is the d energy, and if we take a graph between energy and interatomic distance d, so what happens here? 2n states, 2n electrons will be there. 2n states, 6n electrons will be there. 2n p states, 6n electrons will be there. So, how these are distributed? Okay, let us see. Okay, next, see here, once again come to the example of sodium atom. It consists of 11 electrons, where we have 1s2, 2s2, 2p6 and 3s1 is the configuration. Okay, the single valence electron is in the 3s state. When the individual sodium atom are brought close together to form a solid, what happens here? 3s atomic levels, 3p atomic levels and band overlap. So, 3s atomic levels, the n discrete 3s atomic levels from n atoms split and merge to form 3s energy bands. What happens here? N discrete energy levels of 3s atomic energy levels from n atoms split and merge to form a 3s band. Since the original 3s level can hold 2 electrons, 3s band can hold 2n available states. Okay, has states, and each has contributes to 1 electron each. The 3s band has only half filled. Okay, so what happens here? 3s electron levels can hold 2 electrons. 3s level hold 2 electrons, but in the case of sodium, it is only having 1 valence electron. Understood? So, the 1 valence electron is 2n available energy states. There are 2n available energy states, but only 3s band is only half filled since it has only 1 electron. So, 3p atomic levels. The n discrete 3p atomic energy levels which are empty in an isolated sodium atom also split and merge to form 3p energy band. This band has 6n available quantum states, 3 orbitals, 2 electrons per orbital into n atoms. Okay, there are 6n available energy states, 3p, 3px, 3py, 3pz. Okay, each can accommodate 2 electrons. So, there are 6n electrons are there, but here there is no 3p, so they are totally empty. Okay, no band overlap. In sodium, the equilibrium interatomic distance is small enough that the top of the partially filled 3s band overlaps with the bottom of the 3p band. Okay, the top of the partially filled 3s overlaps with the bottom of the 3p band. This overlap creates a single and continuous conduction band that is partially filled with electrons. This ensures that sodium behaves as a conductor. So, what happens here? The 3p band is completely empty and 3s band is half filled. The half filled 3s band is going to send its electrons to the 3p band, and the 3p band creates a single and continuous conduction band. It is partially filled with electrons. This ensures that sodium behaves as a conductor. So, if there are continuous movement of electrons, then we can say it is a conductor itself. So, okay. So, this is the classification of conductors, conductors, semiconductors and insulators. So, the conductor's band overlap or conduction band is partially filled. energy gap is 0 volts, 0 electron volts, there is no energy gap, and electric conductivity is very high. Copper, aluminum, gold and other examples. Semiconductors, there is the specific class of materials that are known as semiconductors, where they have the minimum energy band gap. The bands are separated by a small gap, is 0.1 to 3 electron volts. Moderate, increases with the temperature. Electrical conductivity. So when the temperature increases, what happens there? The electrons are going to jump from valence band to the conduction band, and there we can have the electrical energy. Okay, silicon, germanium, gallium arsenide, etc. are the examples for the semiconductors. And what are insulators? Bands are separated by very large gap, greater than 3 electron volts of to 6 electron volts. Okay, very low conductivity, essentially 0. Okay, diamond, glass, rubber, wood are the examples for the insulators. Okay, so this is the what is the classification occurs. So this is the energy band diagram. So in a conductor there is no band gap between valence band and the conduction band, and in a semiconductor there is a medium band gap between valence band and the conduction band, where the valence band is having the number of electrons and the conduction band is totally empty. And here in insulator, in case of insulator, there is a large band gap between valence band and the conduction band. So of the order of 3 to 6 electron volts. Diamond, what we can say, diamond, glass, rubber, wood are the examples of the these insulators. Okay, so this is the about the classification of the solids. So in this video lecture, you have learned about the formation of energy bands, origin of band diagram. In the next video lecture, you are going to learn about concept of discrete energy levels. Thank you.